Hello, Mr. Sorrentino here again, and I'm doing yet another one of my videos for the Math 31 course. And this video deals with the last section of Chapter 5, which is 5.6, Applications and Models, Growth and Decay, and Compound Interest. Basically, in this section here, you're going to be reacquainted with a couple formulas. You were taught these two are formulas that you can use for exponential growth or decay, and it really depends on the situation that you are asked to encounter. I provide both of these. The book kind of focuses on this one a lot, and the reason being is that it's the one that's most often used in calculus. The difficulty with it is that the way that the textbook has you address this one is a little sketchy. And that's because what they define this to be as it is the exponential growth rate and instantaneous growth rate. But basically, if a textbook says like you have bacteria growing at a rate of 5% per hour, say. Now, as long as you let your t be in terms of hours, you're good. And they would say that would allow you to say that k is 0.05. And of course, if they eventually say decaying, if they said decaying, k would equal a negative 0.05. And although the answers, are not going to be extremely far off, if you're talking about having numbers in thousands, you might be off by as much as 10, because exponentials, whenever you have a slight differences in values that you're putting into them, you can be off quite a bit. Then, as a result, you could end up having, an answer that, if, you didn't interpret it correctly, that could be, off as far as the math lab, your homework goes. I usually recommend doing this for the percentage, problems where they just say per year. But sometimes you're going to have situations where it says percent per maybe 3 years, They'll say like it grows 5% every 3 years. And then, then you have to do more of the setup that I'm going to show anyway. So I'm going to, demonstrate, how the textbook will do it in some cases and how you're expected to do it. Keep in mind that when you do the homework, and I tried to limit the number of questions that you have to do this with, use the textbook method. In most cases, but when you start taking tests and stuff like that, I'm not going to really care as much, but I am going to show how, just simply making this transgression here is a little bit off, and I'm going to demonstrate that in a moment. But we have this other formula here. This one's a little easier to do because, A is basically your growth or decay um, base. This kind of goes along with most of what we've done in this particular unit because, we had a growth. Remember, our a was greater than 1, so like, you're talking about like numbers that are over 1. If I said like if I had 5% growth, that's 1.05, and if I said 5% decay, that would be 0.95 because basically this means that 100% plus 5%, this means 100% minus 5%. That's what the decay is. So, it's something, but the issue with working with that is making sure you pick the right value for this. Whereas this one here, you're going to see discrepancies between how it should be done versus how they're having you address it, which is basically a shortcut. And it's a shortcut that gives you a good approximate value, but if you want to be more exact, you should really do the two-part process I'm going to eventually be showing. And I'm going to kind of go into that a bit and, be aware of those issues whenever you're doing the homework as well, because if you go with the non-shortcut way, the one that's actually more accurate, my math lab may reject your answer as an answer. So I tried to adjust the settings so that it would have a higher tolerance for that, but it wouldn't allow me to have enough room to, consider to have the point values, the range of the range of values that you could possibly have be wide enough for me to do that. So when we head down into the compound interest formulas, and somehow an errand 4 got it put in here, and this should say 5.2, not 4.2. You have two formulas. The one in 5.2 is the one we're most often used to working with. And so if you have words written like, annually, semi-annually, quarterly, monthly, and these would be the primary ones that you'll see. There was others that we mentioned like daily, hourly, and things like that. But you're not going to probably see most of those. These are the main four you're probably going to see. This is the one you use. This is, the regular compound interest formula. Now, if it says compounded continuously, which basically means you're taking the interest rate, splitting it up into infinitely small parts, and applying it an infinite amount of times. This is the one that you would use. There's not many like bank accounts that compound continuously, but there are things that in biological systems that have continuous growth rates. So, and basically, it compounded continuously kind of gives you the maximum effect of compounding. So basically, if I say, okay, what's the most I could get off of this account? Depending at 5.9% interest, it would depend on how much it's compounded, but if you want to get the maximum possible value, you would compound it continuously. Where these are still standing for the same things. R is still the interest rate written as a decimal, so again, that doesn't mean if you have like 5.9% that's good enough as a decimal, you'd have to convert that to 0.059. A is the amount after years, or we sometimes would call that the accumulated amount. And P is the initial amount, which we would often call the principal. So, so that's going to be a new one's going to be added to the list of things that we are looking to do as well. So, let's get to the first example, which actually does deal with compound interest. Now, one of the things that's also different in this particular chapter is when we go back to 5.2, all the questions you were asked were, written to find the amount that's accumulated, and that's about it. In this particular chapter section, you could be asked a lot for the time it takes for something to happen, as well as, what would the principal need to be in order to get accumulated amount of this much, in this amount of time with this much interest and so forth and so on. So, and that's because now we learned how to handle logarithms and deal with exponential functions in that way, and we could actually solve such equations. Because if you look at this here, you have an initial amount of $10,000 is invested in a certificate of deposit CD with 5.9% annual interest rate. So right now what I would have here is I have A, as far as the information that's given outright, I have A equals $10,000, which is the principal, times 1 plus 5.9%, as shown already, is 0.059 over, now we haven't been told that how many times compounded yet, because that's coming in the next parts of the question. And I have N times T. So there's information here that I'm still looking for. And now, as you look at the first two questions, it asks how long will it take for the investment to double if the interest is compounded monthly, and how long will it take for the investment to double if the interest is compounded continuously. So you can see here we're looking for T. It's always important to know what variable in this formula we're looking to find, because that means that the other information, either directly or indirectly, needs to be given. And that information is given. I mean, as far as N goes in both of these, here, N equals 12. So, I have that part of the formula. And here, compounding continuously, I know that I wouldn't be using this formula. I'd be using this one. So I have, that information here. Now, again, I'm still looking for t in both of these cases, and right now I have two variables. I have t and I have a that's not known. But here's where I know how to figure out what a is. I want the investment to double. I want the accumulated amount to be twice what I started with. So that doubling tells me in both these cases that A is going to equal 20,000. Now, this question could have been posed to you without even having an initial amount given. They could just say, well, how long would it take for it to double? Because this situation here, to go from $10,000 to $20,000, to go from 10 million to $20 million, to go from $10 to $20, it would take the same amount of time in all these instances because that's still doubling. And basically, the amount you might be increasing by on more of a linear factor is, bigger for bigger numbers involved, but the percentages would still be the same. So with this now, I could now answer these questions because now I can say, okay, well, here I have 20,000 equaling 10,000 times 1 plus 0.059 over 12 to the 12t power. And so I want to start solving this and simplifying along the way. I'm going to divide both sides by 10,000. That's going to give me a 2. And if you have a situation where it just said, okay, there's no initial amount given, you could simply start with this equation here and realize, okay, well, would be what determines what that rate is. And I'm going to simplify this inside here. 1 plus 0.059 divided by 12 is 1. I don't have the eraser there, so 1.004916 repeating. Now, when I deal with problems like this, I make sure that I keep the full amount on my calculator. I'm not going to start rounding here. It gets a little sloppy to try to do some of the things we had done in the previous problems, but for this point right here, doing that's a little bit impractical. So I'm going to make sure that either by using the previous answer command, which is hitting second and the negative button on a TI calculator, or using the memory feature, which basically using the store feature, you can store the number in for any variable and make use of that. And I'm not going to go into that stuff so much. You can actually keep the number as accurate as possible, because even if the calculator is showing you about 8, 9, 10 decimal places, it has many, many more stored in its memory and how it was calculated. So it's going to give you the most accurate answer if you keep it to completion. I may not want to write out all the numbers myself as I do this, and I still want to write this out as I do that to show my work and follow my steps, and maybe go back and give a rudimentary check to make sure everything's working out with the decimals I have. But using the calculator to its fullest capacity is probably the best thing to do. So anyway, to make more room for this part of the problem, I'm going to scooch over here, kind of start with that formula there. So I have my 2 equaling 1.004916 repeating to the 12t power. I want to solve this equation. I can rewrite this as a logarithmic equation. However, if I'm writing it as a logarithmic equation, I'm going to have a base 1.004916 repeating. That gets kind of sloppy to write. And also along with that, I'm probably going to need to use a change of base formula anyway. So what I'm going to end up doing here is I'm just going to say, okay, I'm just going to apply a logarithm on both sides. Because what that will do is that I'm going to have the log of 2 on this side, and I'll write it as I would put it in the calculator, realizing that's just going to be a number. I'm going to have, well, since I have a logarithm here now, this 12t can be brought in front. So 12t times the log of 1.004916 repeating. I want to solve this equation. I can, out of this, I can actually factor out a t and say t times 12 times the log of 1.004916 repeating. Recognizing now that this is just going to be a number, all of this is just going to be a number. So I basically have a number equaling t times some other number. So obviously to solve for t, I'm going to divide both sides by that 12 times the log of 1.004916 repeating. So I would have this. And again, on the final exam, you might be asked to provide the logarithmic form of the answer that you would plug into your calculator to get the final result. And that's what this would be. So now if I put that in my calculator, I'm going to get t equals 11.78 years. And actually, I should technically be a wavy equal sign because it's approximately equal to. So, that's the answer I get for this one. Now, compounded continuously. Compounded monthly, if you remember when we were talking about that, once I'm up to this point here, there's not much of a difference between monthly to daily, to hourly, and things like that. So I'm not expecting a huge difference between having it compounded monthly versus compounded continuously. I would expect the answer for the part B to be maybe slightly shorter than 11.78 years, but it's not going to be probably significantly so. And again, I'm just going to use the information that I have, and since because of the doubling, I now know again that that's going to be 20,000, I should say, equaling 10,000 e to the 0.059t. I would divide again both sides by 10,000, and I would get 2 equals e to the 0.0059t. One of the good things about using situations where there's e involved, you don't have to sit there and worry about logarithms and the change of base, because there's only one logarithm you would use, natural log. So to move further into this question, I would say that the equivalent logarithmic statement would be that 0.059t would equal the natural log of 2, and t would equal the natural log of 2 over 0.059. And when you work that out, you get about 11.75 years. So again, as I said, not a major difference, but it is slightly shorter. For part C, we want to figure out an annual growth rate for both of these situations. So I'm going to have a situation that represents A again, and one that represents B again as I do this work. Basically what this is asking you to do is figure out what is the percentage growth in a year's time based off of the fact that we do have a 5.9% annual interest rate, but with the compounding, I'm going to actually be adding more than 5.9% to my initial investment in a year's time. I want to figure out what that percentage actually is. And so what I need to do is figure out basically a final amount minus the original amount. I want to divide that by the original amount and multiply that by 100%. And that's going to be the same in both cases. I'm going to take the final amount, or the accumulated amount, subtract away the principal, and then divide by the principal and times 100%. Now that 100 times 100%, when we use that, oftentimes in math, that means that we're going to be, multiplying the result by 100, so we can present it as a percentage rather than as in decimal form. So getting back to A, since it's an annual growth rate, I know that t equals 1. That's going to be true for both of these situations. And so I want to see what the accumulated amount is when I have 10,000 with that 0.059% interest rate, compounded monthly. And technically I put times 1 out here, but 12 times 1 is just 12. So I'm just going to keep that. And so the final amount for this ends up being approximately $10,606.22. And since we're dealing with money here, it's okay to kind of round off the decimal places. Technically, you should kind of keep the exact account in here until you calculate what the percentage is. But my annual growth rate now is going to equal, well, if I take this amount and subtract away 10,000, I'm just going to have $606.22 over that 10,000 times 100%. And that equals about 6.0622%. So not significantly more than 5.9%, but it's still more than 5.9%. Obviously, the more money you have in the account, the more of a difference this will make. I mean, as far as going up is actual value, but percentage-wise, again, this is, that's the same thing as if like, like we said with doubling, if I double $10 to 20, it's the same, it's going to take the same amount of time as doubling 10 million to 20 million. It's just I have much more money being added to the account, but percentage-wise and proportional-wise, they're the same proportions. So, as for B, let's scooch over a little bit. I'm going to do the same thing, except now I'm going to use the formula. A equals 10,000 e to the 0.059 times t, which would be 1. So A is approximately going to be equal to $10,607.75, which means when I use the formula and do my annual growth rate, I'm just going to say AGR for this, equals, it's going to be that 10,607.75 minus the principal of 10,000 is going to give me 607.75 over that original 10,000 times 100% is going to equal 6.0775%. So again, between these two, the annual growth rate is about 6.08%, whereas the other one was 6.06%. Not a huge percentage difference, but again, with bigger amounts, that would mean something more significant. So, those are the kind of questions you could be asked dealing with compound interest. So be aware of those and know how to handle those. For example 2, we're going to kind of look at the two different types of formulas we have for any other type of growth or decay, and see what the difference between them is. Know some of the terminology, and be aware that the shortcut that the textbook does provide will give you approximately a somewhat good enough value in many cases, but it's not going to be as exact as other methods. So I'm going to show that as well. So let's have a look at example 2. Now, I was looking at example 2 here. Keep in mind that a lot of the problems that you're going to be given are going to say like 5% per year, 5% per day, 5% per month, whatever. Whereas this is saying 5% every 8 years. When you start having situations like this where it's not per year, per month, per day, it's not a percentage per one single unit of whatever it is, you're going to have to use a two-system setup. Or I should say two-step setup. Which means it's going to take you 2 steps to get the problem done right. Because in step 1, you're going to find, depending on which formula you're using, either A, if you're using the formula you suggested in A here, or you need to find what K is if you are if you're using the second formula that's indicated in B. And then this will lead you to having a formula with enough information in it, and then that lets you go to 2 where you can actually answer the question. In both these cases, I had to set up the equation a certain way the formula a certain way, solve it, get what I need to get the formula, and then I'll have the work with that. So in part A, they say find the formula of the function that describes the situation in A equals P A to the T format. So this is an instance where we're going to need to find out what A is. Now, if this had said 5% every year, if it had said that instead, like 5% per year, then A would have that would have been really simple. A would be 1.05. That works out really nicely. However, again, you have to remember that this isn't the way that it tends to work out very well, and with this, because now it's 5% every 8 years. So I actually have to go through a process to figure out what A is if I'm given this kind of situation. And so for this one here, I had to actually set this up and say, okay, well, I'm going to first start off with knowing what I know here. A equals P A to the T. And basically what I'm told is that in 8 years' time, my final amount, given this initial value P, now I could put a number in there, any number I pick, and since we're dealing with percentages, it'd be 100. But it stands to reason that if I start with this amount P, then A would be 105% of that initial amount. And then when I go through the solution process for this, I could say, okay, well, the first thing I would do is divide both sides by P, because I'm trying to figure out what A is, and I would end up with A to the 8th equals 1.05, and then A would be the 8th root of 1.05. Now, for purposes of writing formulas and stuff here, I'm going to evaluate what that is. That's 1.006117. Good enough. And so my formula ultimately for this is going to be A equals P 1.006117 to the T power. When I do the same thing for B, I'm going to start with this A equals E to the KT. I don't know what K is. I do know, again, and that's PE to the KT. I do know that after 8 years, with an initial amount of P, again, I'm going to have 105% of P for my accumulated amount. And so what I basically have at this point, when I divide both sides by P again, is that I have E to the 8K equaling 1.05. And so to solve this for K, 8K is going to be the natural log of 1.05, which means that K is going to be the natural log of 1.05 divided by 8, which is, again, for formula purposes, is approximately equal to 0.006098. And so the formula that I would use if I'm using this one is A equals P E to the 0.006098 T. Now here's the difference between an exponential growth rate and an annual growth rate. First of all, in many cases, your textbook treats them as being the same thing. So if it says 5% per year, for instance, they'll say that that's the same thing as the exponential growth rate. The exponential growth rate is K. And as we see here, that's 0.006098. And if I wanted to write that as a percentage, that would be 0.6098%. So that's how much your investment or this population is growing each year, or over a period of time. It's not actually per year. It's basically, it's kind of hard to explain what the exponential growth rate is. It's not really an annual growth rate. The annual growth rate comes from actually A. The A equals 1.006117, which, if I wrote it as a percentage, is 100.6117%. Well, that's an amount that is kind of telling me what the growth rate is, because this is the growth. I mean, anything over 100 is how much it grew. So the annual growth rate is actually 0.6117%. As I said, though, word of warning, your textbook treats these the same. They aren't. They really are not the same. So as a result, especially when you start dealing with situations where you're talking about bigger values, you have like an initial amount of like 1 million, and you're looking for amounts or times and things like that. Um, this percentage difference. I mean, if I round both of these off to two decimal places, it's 0.61. I mean, yeah, the annual. I mean, the K is a good approximation of the annual growth rate, but it really isn't the same thing. Just be aware of that. If they when they ask for an annual growth rate um, for um, problems that are in your My Math Lab homework, or they tell you that you have a certain percentage per year, make sure that if you're using the e to the kt, that you are treating it the same as that. But technically, it shouldn't be. Um, Now, with both of these, I can figure out what the doubling time is. So the doubling time would be. So as I work on this doubling time as well, I'm going to be showing you how to do this using either of the equations, because in both cases I've already found out a good formula to use. I have this one, if I'm using the formula, or the A equals P times A to the T format. And so I could say, well, I could use A equals P times 1.006117 to the T power. Or I could use the one we just got from part B, which would be A equals P e to the 0.006098 t. So, in both these cases, it doesn't matter which one I make use of, and you're going to see this as we do the calculations. Now, I'm looking for a doubling time, and that means that I'm looking for, I want to find t when my final amount is equal to 2 times my original amount. So I'm just going to let A equal 2p for this one. Now a couple things happen here. I need a t there to the t power. Still in the exponent. The p's would cancel out, because the first thing I would do is divide both sides by p, because I can't turn an exponential function or an exponential equation into a logarithmic one if I have anything being multiplied to the base. So I would typically divide both sides by whatever is being multiplied to the exponential. And all it's going to do is cause the p's to cancel here. And the reason why, again, I'm using p's is because I didn't define what the starting value was. If you don't like using these extra variables, you can certainly just decide to let p be, whatever number you want it to be. Since a lot of percentages come into play, I usually recommend using 100, and then adjust accordingly. So if you let p equal 100 here, then A would have been 200, and you still would have gotten to the same point where this 1.006117 to the t power equals 2. So it doesn't matter if you set it up right and you truly doubled the initial amount to get to the final amount. You're going to end up at this point anyway. Now, I'm just going to apply a logarithm to both sides of this, because now I'm going to have t times the logarithm of 1.006117 equaling the log of 2. And this is log base 10 because I'm not putting a base on there. And so t is going to equal the log of 2 over the log of 1.006117, and that's going to approximately be equal to 113.7 years. I could do the same thing with this formula over here. Again, my final amount would be 2 times my original amount. I would divide both sides by whatever that original amount was, because again, even with the base e, I cannot turn it into a logarithmic equation until I just have the exponential and the base and its exponent. The only thing that's going to be different here, and there should be a t up here again. I keep forgetting to rewrite the t. The other thing that's going to be different here is, since e, this is I mean, all I have is the base e. It's probably just best to use a natural log. So I'm going to have 0.006098t equaling the natural log of 2, which means t is going to be the natural log of 2 over the 0.006098t, or no, t's on the other side. And you would find out that that's approximately equal also to 113.7 years. So it doesn't matter which formula you utilize for this. It's just you need to make sure that you keep it straight, and you've already set it up. You've either found out what the base A is if you're using the one outlined in A, or you've found out what K is in the instances where you're using PE to the KT. Again, be aware, again, the textbook treating the exponential growth rate K and the annual growth rate as being the same thing. Yeah, sometimes they're very close, but they're not exactly the same thing. In some cases, you'll get values that are close to each other, and others you may not. So, for the My Math Lab things, keep that in mind. And when they say, like, if it's growing 5% per year, what's K? K is going to be 0.05 for the book's purposes, but it's actually not going to probably be that. It's probably going to be a little bit off of that normally. So it really depends on what the period of time is too. A lot of the ones they have in the textbook are going to usually say it's going to be a rate per year, per day, per hour. They do throw a few problems at you though that have per 8 years, per 4 years, that sort of thing. So let's get in and do another example. Now I'm not going to do it both ways. I'm just going to show you an example 3. We're asked to do it using the PE to the KT. So let's have a look at that. So we have this problem here. An unknown substance decays at a rate of 10% every 3 days. What is the half-life of the substance? Now again, you're not being told here what the original amount of the substance is. And again, it really doesn't matter. I mean, it's losing 10% every 3 days. So if I had 100 pounds after 3 days, it'd be 90 pounds. If I had 10 pounds after 3 days, I'd have 9 pounds. I'm losing 10% each time. So it doesn't matter, what values I use. So now the thing is, again, one of the things you sometimes run into is that students will think that, since I'm using this A equals PE K to the T power, they want to say, well, K is going to be, equal to -10 or -0.10 because that's 10%, over 3, which is a negative 0.03 repeating. And some of the things that the textbook is leading on with would make you believe that is true. And the thing is, they're using a rule that only works as long as you're dealing with very small percentages. And very small percentages, you're talking about usually 5% or less. And they're applying it to a situation where, you have percentages that, are, sometimes more than 5%. Um, so you have to be careful with things of this nature because the textbook is using something that is a good approximation as long as you have a small percentage growth or decay. If you get over a certain percentage, the discrepancy between using K, estimating K in a manner like this, and how to actually go about doing it is going to start causing a much bigger difference, especially when we're dealing with, percentages and large amounts in some cases. So I'm going to use a two-step process. I have this formula I want to use. My first one is I'm going to find K. I'm going to expect it's going to be somewhere close to this. And by the way, that's negative 0.333 or 0.333 repeating. But I'm going to expect it's going to be close to that, but it's probably going to be off ever so slightly. So let's have a look at this. I'm starting with an original amount. I don't know what it is. I don't know what K is yet, but after 3 days, I'm going to have 10% less. Now, the thing else to remember about these formulas, especially for decay problems, if I'm decaying at 10% every 3 days, that means after 3 days, I'm going to have 90% left. These formulas always deal with the amount present, not the amount lost. And so, just like when we did the percentages before, like for when we had a doubling, or if we increased by 10%, we would have 110%. Well, in this case here, we have 10% less, so the final amount is going to be 0.9 or 90% of P. Now, of course, as I go through to carry through the solution process to figure out what K is, this would cancel. I would have now that 3K would equal the natural log of 0.9, which means K would be the natural log of 0.9 over 3. And if you work that out, you get it to be approximately negative 0.03512. So as you see, close to what this was up here, although it's written sloppily. I'll write it a little bit better. Although close, not exact. And sometimes that difference can cause some major discrepancies when you answer questions like this. When you're looking for times, it's usually not going to make a big deal, but if you're looking for amounts, that's going to cause a bigger situation. It's going to cause a bigger issue. So now we're actually able to do part 2, and we're going to answer the question. Because we now have a formula. We now have the complete formula, A equals P e to the negative 0.03512 t power. We want to figure out what the half-life of the substance is. The half-life, if you ever taken a science course or read through the textbook, because they define what a half-life is as well. A half-life is the amount of time. So this is asking us to solve for t. It's the amount of time it takes there to be half the original amount. The original amount being p here. So for me to solve this, I'm going to have to let a be 1/2 of what p was, half the original amount. So again, if you're using your own numbers, you would have taken half of whatever you let p equal, and you would get to the same point whenever you start carrying through your work. You would divide both sides by the original amount, whatever you allowed it to be. You would still get 1/2 equals e to the negative 0.03512t, and I would natural log both sides, so I would have that negative 0.03512t is going to be the natural log of 1/2, which means t is going to be the natural log of 1/2 divided by negative 0.03512, and that's going to be approximately equal to 19.74 days. And so every 19.74 days, this amount of substance, it becomes half the amount it was 3 days ago. So logistic growth, they talk about in the textbook. I mean, you may see a question come at you regarding it, because it's really not going to ask you to do a whole lot. It's not going to. It's going to ask you to do some plug and chug. It's going to ask you to do some things where you may have to manipulate the overall equation and solve for something. So we're going to see some examples of this. So when we look at this one here, and logistic growth is basically, as it's explained, is a growth that realizes that, in biological systems, I could have something start off with an exponential type growth. However, usually since the amount of space is not increasing, if there's a forest, and the forest, as long as it's not being cut down or anything, if it's left alone, it's going to stay the same size. If I have a population of deer in it and they're growing, well, sooner or later, if they're left to keep growing, eventually what's going to happen is that there's not going to be enough food in that forest to feed them all, so they're going to start dying off, and it's going to start stabilizing how many can actually be kept in there. So that's more of a logistic growth, where it kind of says, okay, well, we start off having like an exponential, but it kind of veers off after that. And they often have this format where you have some kind of constant number over, some expression involving, and most of the time it's going to be e to a power, but sometimes they will have another base here. And notice that is a negative exponent up here overall. It's a negative 0.5, or oftentimes it's going to be a negative number times t. You want to keep that in mind, because some of the things that are going on here, you want to be aware of about how to handle this. So for instance, we have this function p of t, which equals 3200 over 1 plus 5.40 e to the negative 0.5 t, where t is the number of months after it is stalked. And so they're saying, okay, based off of this logistic function, which would probably gotten off a computer or a calculator or something, how many fish were initially in the lake? It's just we're not being told that. Well, that means, from our function usage before, that means we're essentially looking for p when the time is 0. So that's going to be 3200 over 1 plus 5.4. Really don't need to put the 0 there for my writing purposes. This 0. That's just there to show how that was rounded to that place, and so that we're starting off rounding, having some numbers with 2 decimal places. Therefore, it's probably best, for me to eventually maybe round to 3 if worse comes to worse. However, since we're talking about the number of fish in a lake, I'm going to probably want to approximate it better by rounding it off. Mostly because of the fact that, what does it mean to have 0.8 of a fish? Does that mean a fish and its tail cut off, or what does that? Doesn't really make any sense. So, just how many fish approximately are in there, it might be better to round it to the nearest whole fish. But what's nice about this is, it's pretty easy to do. Since I have an exponential function here, this becomes 0. Anything to the 0 power is 1. So this is basically, all of this over here is basically 1. So I basically have 3200 over 1 plus 5.4, which is 3200 over 6.4, which is equal to 500. fish. So there were 500 fish initially in the lake when it was stocked. They stocked it with 500 fish. What is the maximum number of fish that the lake can sustain? Now this one's a little bit problematic because what I want to do is figure out what P of T is. And you'll start using other notation for this as you get into a little bit of pre-calculus and especially in calculus. As T approaches an infinite amount. As we keep going and going and going and going, assuming that we're not going to stock it again, which isn't really what happens typically. But if we kept going and going and going, what's the maximum number of fish that the lake can sustain based off of what this function's telling us? Because this function would eventually level off at a value, at a y value where I'm not going to go past that. It basically does have a horizontal asymptote. And I want to figure out where that is. So I had to think a little bit about this. Well, I was going to say it's the maximum P of T would be, well, I'm going to have the 3200 over 1 plus 5.4 E. Well, let's think about what goes on with this. Let's not even go with that exponential there. This is what they want you to do with this, to think about what's going on here. If I have, it's a side note here, e to the negative 0.5 t, and I put a value in there. If we put the 0 in there, that's 1. If I put 2 in there, I get smaller. I put 3 in there, I get smaller, because this is basically reciprocating. This is basically saying I have 1 over e to the 0.5 t power. Now, if t keeps increasing, this denominator keeps increasing in value, but the top doesn't. The top remains 1. So if I have a 1 on top and I have a number that keeps getting bigger and bigger and bigger on the bottom, what is the value of this fraction going to approach as t keeps getting bigger and bigger? And so that basically becomes 0. So this exponential thing, when I have t approaching infinity, is just going to become a 0. And that means that it's going to, in this case here, I'm going to have 3200 over 1 plus 0, which is 3200 over 1, which is 3200. Please, please, please do not assume that the number up here is always going to be the maximum number of whatever they're talking about. This function down here doesn't have to have a 1 in this position. So keep that in mind. The other thing you have to remember is if I'm looking for the maximum number, that means t is going to infinity, and the exponential portion will be approaching 0. So that's what I want to, I want to take the exponential portion and replace it with a 0. So 5.4 times 0 would be 0, and 1 plus that would be 1. So it works out in that way. Now, as far as, the question in C is asking, it's asking essentially, okay, what's P of 11? So this one here is just more of a plugging it into your calculator correctly. Making sure you use your parentheses correctly and everything. And so if you do that correctly, you would get about 31 fish, rounding it off. And now it says, how long will it take for the population of fish to reach 1,000? So now we're saying, okay, we know that P of T equals 1,000. And of course that equals 3,200 over 1 plus 5.4 e to the negative 0.5 t. I want to solve this equation for t because it's asking for us for how long, so it's kind of an indicator that t is what we're looking for here. And I want to also keep in mind that, I have a fraction on, basically something written as a fraction on the right. I can rewrite this as a fraction, and I can cross multiply. So I'm going to have 1,000 times 1 plus 5.4 e to the negative 0.5t equals 3,200. When I distribute the 1,000, I'm going to have 1,000 plus 5,400 e to the negative 0.5t equaling 3,200. I would subtract 1,000 from both sides. I would divide both sides by 5,400. And it would basically reduce to a fraction of 11 over 27 when I simplify the fraction completely. I need to get rid of the exponential base e, so I'm going to turn this into a logarithmic equation. So negative 0.5t equals a natural log of 11 over 27. And t is going to be the natural log of 11 over 27 divided by negative 0.5. And when you calculate that out, it's about equal to about 1.8 months. So, and basically that's how long it takes to double, because we learned that we had 500 fish before when we started. It doubled, so that would only take about a little less than 2 months for that to happen. But, if they're left unchecked, that they only get so big. And that's kind of showing you that it starts off growing pretty exponentially. They grow pretty fast, but it eventually does taper off. Now the last part of this, um, I'm going to show you how to do it because in some courses you might know it might be beneficial to you. You're not going to really be tested on doing many regressions going beyond linear. And even with that, you're not going to be asked to do it on a final exam or anything either. And I'm going to kind of walk through this. You have some of this explanation here and some of the graphics and things of that nature. I'm not going to go through all that. I'm going to kind of demonstrate it so you can see what we're talking about here. So I'm going to bring up my calculator. And so you're basically told that in an art class, students were tested at the end of the course on a final exam. Then they're retested. Then they were retested at given with an equivalent test at subsequent time intervals. Their scores at their time X in months are given in the following table. So essentially, they're trying to measure retention. How much was remembered. So 1 month afterwards, the average score was an 84.9. 2 months later, it was an 84.6. And so they're asking you to do three things. Use a graphing calculator to fit a logarithmic function to the data. Use the function you obtained in Part A to predict the test score after 2 years. And how long will the test scores fall? After how long will the test scores fall below 82%? So let's have a look at this. And I took some shortcuts already with this, and in the interest of time, I've already loaded this table into this. So if I turn it on, let's clear this a little bit. So if you look under stat and under my edits, I have the table already entered in the same way you see it listed here. Of course, I can't put the zeros at the end because even if I do, the calculator is going to usually cut them off anyway. And so the first thing they ask us to do is to use the graphing calculator to fit a logarithmic function to the data. So we want to do a logarithmic regression. So I'm going to go to here. I'm going to go under calculate, and the ninth choice down, it says LN, which is your log base E regression. That's really the only logarithmic regression this does. I know Excel, I believe Microsoft Excel will do the same thing, except I think it does a log base 10 instead. I'm not going to, guarantee that, but from what I remember, it does. So, depending on what you're using, you may get something different here, but if you're using the calculator, you're going to get a natural log regression, which means we're going to fit a function involving a natural log of x to this. So I'm going to hit that. My x and y's are in L1 and L2 already. Store the regression equation to make my life easier for part B and even a little bit of part C. I'm just going to say, okay, put this into y1. So when I eventually hit this button here and go to my equation, I might want to graph it, it'll go there. And so it's giving me the information. I mean, I could write the equation at this point based off of this. So if I wanted to write an equation here, now one of the good things about it, the calculator has all this saved, but if I wanted to write this, this is going to disappear a little bit as I write this because, you know, that's the way it works. I would have basically my score, which I'm going to say is, I'm just going to call it S of X, which equals my Y's. And that's going to be an 84.9435 minus a 0.5413 times the natural log of x. That would be my logarithmic function that fits to this data best. As far as the other things go, I mean, these two things I can answer pretty easily with the calculator. This one, if I want to be maybe be a little bit more accurate, it might be a better idea for me to, solve the equation algebraically, which I'm going to show that too. But, the first question is really easy. Use the function you attain to predict the test score after 2 years. So if they keep getting tested on this exam after 2 years, if it's following this pattern, we would expect it to see, we want to see what the score is at that time. 2 years, remember we had times in months, so that means our x value in this instance is 24. And so what I want to do is going back to my calculator, now again, the regression equation is already in here. Notice there's already more decimal places here. And again, there's a bunch more showing here, but there's even more stored in the calculator's memory. So I'm going to get a pretty accurate one if I make use of this. And all I'm just going to do is go to variables. And we did this earlier in the course. The y variable 1, because that's where the formula was. I'm just going to plug in 24. And as you can see, I get about 83.22%. Or maybe just go one more, 82.223%. So that's what I would put down for this, about 83.223%. That's what I would expect the average score to be after 2 years. Them taking if they were doing this. As far as when was it going to fall below 82%, I could do that graphically. And we've talked about this earlier in the course as well, but I could do this graphically just by saying, okay, well, I have this graph here, which is going to be the function itself. I want to see, okay, when does it become 82? And so again, I might want to set my window so I can see what's going on here. I know I'm not going to really have any situations where I'm going to have negatives here, so I still want to see the axis. So I might say, okay, go to -1 for that. Maybe go to 20 for that because we already had something going on at 24 months or that sort of thing. Maybe a little more than that. Actually, let's let this go for reasons why. And we'll go by 50s on this. And my y min, I'm just going to go to -1 on that because, again, I can't have any. I just want to see the axis. I don't want to. I'm not going to have any negative values or negative scores. I can't score a -5% on a test. That means I missed more than I lost. I missed. That's like me missing like 7 questions out of 5. So. The Y max. Now we're starting. I mean, as we look at this, looks like the highest score is probably near the 85. So maybe just say 85, and go by 5 should be okay. And if I graph, what I have there. This is my logarithmic function. and there is my line when it's 82%. And right now I'm not really getting a good picture of what's going on here because it's, they're so close together at this point up here that I can't really see what's going on very well. So what I'm going to do is come back to here at my window. I know I'm looking to see when it becomes, the Y value becomes 82, because that's what the percentage is. So maybe let the min now be 81. Let the max be 83, putting 82 right between them, and let that go by 1. And then we'll see what the graph looks like now. So there's my logarithmic function. Sometimes it's better to play with the window than play with the zoom features, because the zoom features kind of keep the same aspect ratio. So if it looks really flat and you can't see anything going on, then it's going to be the same whenever you zoom in as well. And I can clearly see where the intersection is at this point. So now, what I'm going to do is I'm going to go to my calc menu. That's me. There we go. Now it's going to ask. Okay, there we go. I'm looking for the intersection between these two lines, so it's going to first put me on the blue curve at y1. I have this set up, so that I'm looking for the intersection. So I'm just going to just choose this curve, and then I just want to basically, I can move it close to where the intersection is. Doesn't really matter so much. And as you can see, I get about 229.99906, so about 230 months altogether to solve this. Now, what I can do also is I could have done this algebraically. And so if I have this function right here, now I'm using 4 decimal places, so it might be off a little bit when I do my calculations. I'm looking to see when 84.9435 minus 0.5413 times the natural log of x is going to equal 82, and then I would round up to, obviously say, okay, well, after that it should probably, be below that. So I subtract 84.9432 from both sides, and I get negative 2.9435. Then I divide both sides by the negative 0.5413, and I get 5.4378. And then I would take the exponential of both sides, so this would be e to the 5.4378. Make that look more like an e. There we go. And that would be approximately equal to 229.94. So, even with this, I would still say, 230 months, because we're saying here at 229 and very close to 230, I would be exactly at 82. At the rate this is going, and in fact it is declining each time, I would expect that, if I go, the next full month, I would fall below the 82 mark. And so that's how you could use your calculator in these instances, and that brings us to the end of this video. If you have any further questions, please make sure to bring them up in class or see me during my office hours. Until I see you at one of those places or until the next video, have a good day. Bye, everybody.